I will mainly talk about how can we come up with a solution trying to fix CO2, in particular using photoelectrochemistry. And today I will more focus on an integrated approach. And the integrated approach is really sort of based upon what's happening in natural photosynthesis. And this particular concept, you can consider this is essentially nanoscopic photochemical diode, and a million of them putting together. Photon goes in, they cannot escape until they get absorbed by semiconductor. So that's another major advantage. Shortage of photovoltage can be sort of rectified that by introducing a biological catalyst. Okay? And, there are multiple steps of this sort of chemical reaction. Once you have the acetate, you can do many of these sort of downstream upgrade into different product. In order to improve on the stability, we do need, again, inorganic catalyst with low overpotential and high selectivity.
We'll talk about the photocatalytic hybrid semiconductor metal nanocrystals for solar fuels. Over the years, we've been able, as a community, to achieve control over shape, like nanorods, nanoplatelets, heterostructures. And the advantage of the quantum dot approach is, of course, the ability to tune properties, the emission color being the most obvious one through quantum confinement. The reactions I've been focusing on are mainly so far water splitting. And if you think about it, there are two steps in this type of process. First of all, the charge separation step, and then the reduction step. The merging of the nanocrystals with a photoelectrochemical cell is a point which we would like to explore. The idea of a full reaction cycle that can consider also production of valuable chemicals and not necessarily the water splitting is also another important direction.
I will be starting talking about water splitting, and my idea was to tell you something about the material science and what is needed. So we need about 10 tons of water, clean water, to get about 1 ton of hydrogen. And then, of course, we need to be able to store it and transport it. Ammonia could be one of these energy vectors. Really want to make an energy transition based on green hydrogen, and we see how much iridium we have in the world and how expensive it is. It will be very difficult to justify this. So the synthesized materials are pre-catalysts, they are metastable, and they adapt to the reaction environment. Only when you get this type of rational catalyst design, you are going to be able to improve the material's stability and, of course, also to decrease the process cost. They're actually going to be key to understand degradation, for example, of the performance, or even the promotion effect. So it depends on very, very minute changes, for example, in the impurity level within these electrolytes.
My work today that I'm going to talk about is really focused at the integrative level when we think about energy transitions. So reducing CO2 emissions from energy and industrial systems requires working on multiple fronts. Both the work of the Indaba Partnership and this project are very much focused at the moment on processes for reducing CO2 emissions from iron and steel making. In each of these cases, the cost and the emissions profile depends significantly on your use of hydrogen. The tax credits under the Inflation Reduction Act seem like they would cover much of the variable cost of the steel transition. There seemed to be openness among the industry representatives to green steel production tax credits or even a CO2 fee in the United States. Our analysis suggested that natural gas DRI is actually maybe not a bad route to be pursuing with the flexibility to move to hydrogen or add CCS.
I'd like to start with the very well known that first of all, last year we had again an all-times high in energy consumption. We have to close this gap. We have to get rid of all this gray part that especially rare earth elements and the PGMs, the platinum group metals, are key to consider from the very first minute because they are rare and they're expensive. Finally, yes, we have to talk to our politics in terms of regulatory frameworks that they are set nicely. And the last word, of course, is about international research. The task is so complex and so big, so we can only work together and try to realize solutions.